Hello, everyone. Thank you for joining us today and welcome to today's webinar from our Standards Activity Board series. And today's presentation is from the IEEE 802.11 Working Group. My name is Edward O. I am the Vice President for Standard Activities of the IEEE Computer Society. Before we get started, I would like to address some housekeeping items. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. The speaker will answer as many questions as possible after the end of his presentation. When submitting a question, please reference the slide. A copy of the slides and the recorded webinar will be emailed to you in the near future. Circling back to today's presentation, is about the Wi-Fi. Standard 802.11 is one of the many standards founded by the IEEE Standard Association and managed by our Computer Society under the Landman Standard Committee. Wi-Fi is important to many of us, and I suppose many of you may be actually using Wi-Fi to connect to the computer and also to listen to this webinar. And for 802.11 working group that focus on the development of Wi-Fi standard, they actually develop many cutting-edge, high-quality, and market-relevant standards for wireless local area networks. And you actually may hear lots of different useful and practical applications and also different branch name like Wi-Fi 6, Wi-Fi 7, and our speaker may mention later about Wi-Fi 8. So in this webinar, we will have a live discussion with our Wi-Fi expert, Dr. Robert Stacey, who is also the chair of the 802.11 working group about these exciting topics. Robert is, just I mentioned, currently the chair of 802.11. He has been an active participant in the standardization effort and different industry consortium, starting from the development of the 802.11n about 20 years ago in 2002. And for most of the time, Robert was employed by and is currently employed by Intel and has worked internally with their Wi-Fi products. Hey, Robert, good morning. Thank you so much for accepting our invitation to deliver a presentation to our Computer Society members. You now have the floor to share with us the latest, the hot topics in 802.11. Thank you, Robert.
Thank you. Thanks very much, Edward. And it's a pleasure to be here. We had a little discussion before we joined the actual live, and Edward recommended that I point out what these devices are in the back of my screen here. This one here is one of the original IBM PCs, and this one here is one of the original Apple Macintoshes. This is the 128K Apple Macintosh, and they both still work. I occasionally show them to my kids. But anyway, since I was presenting on to the Computer Society, I thought it would be relevant to sort of mention that. So let's dive into my presentation. And I'm going to share that. Let me just share my screen here. This is the one I want to share. And this is the presentation I want to share.
Yes, and I confirm I can see your presentation, Robert. Thank you so much.
Wonderful. Thank you. Thank you, Edward. So my name is Robert Stacey. I'm the working group chair, the 802.11 working group chair. And in this presentation, I'll provide an overview of the 802.11 working group. I'll provide a brief history of the 802.11 standard, and then we'll get to the main topics, which are a review of the current activity in 802.11. So 802.11 is part of the 802 family, and I put what could be considered an org chart up there. So the focus in the so it's part of 802 local and metropolitan area network standards committee. So under that, you'll see the 11th working group deals with wireless LANs, wireless local area networks. The ones prior to that all dealt with wired LANs, and then there have been there are still a number of other working groups active. You might recognize .16, That's actually in hibernation at the moment. They developed WiMAX. There is still some work going on .16, but it's being done in the .15 work group. .15 is where you would find ultra wideband and some of the other specialty networks. And then, of course, you're probably all familiar with Ethernet, and that's done in the .3 in the 802.3. And another thing to note about this group is that we deal with the data link and the physical layer, and we leave the upper layers to other groups, primarily the IETF. Okay, so this is a history of the .11 802.11 standard. The first version of the standard was published in 1997. And there was a revision of that came out 2 years later in 1999. And you can see the history since then. These are all the revision projects. So in each revision project, so a revision of the standard is published and then we amend it. So then we have a number of projects in flight at one time, amending that base standard. And then the next revision project will roll those amendments into the base standard. So so this graphic here is trying to show you the various revision projects and the amendments that were rolled into those revision projects. And we've recently completed or recently had approved the 2024 revision of the 802.11 standard. And you can see that the 2024 revision rolls in 802.11ax, for example. This slide shows our standards pipeline. So this is so an overview of what we're currently working on. So to begin with, new ideas are presented in the Wireless Next Generation Standing Committee, and we refer to this as WING. With sufficient interest and working group approval, these new ideas evolve into either a study group or a topic of interest group, and that would be the next column you see on the left there. A study group develops a project authorization request, known as a PAR, which is necessary to revise or amend a standard, and a topic interest group develops a report. And then with PAR approval, a task group is created to develop a draft standard, either a revision of the standard or an amendment to the standard. Once the task group has an initial draft, the draft is balloted in the working group, and that would be the next column you see there, working group letter ballot. There are usually multiple rounds of balloting as comments are addressed and the draft is revised. And then after approval by the working group, the draft proceeds to balloting at the Standards Association level, the IEEE ESA level. Again, there are multiple rounds of balloting, and as comments are addressed and the draft is revised, the draft is then presented to the Standards Association Standards Board for their approval, and if approved, it's then published. It goes through publication editing, and it enters it's made available on the IEEE ESA website. And as I mentioned, we currently have the well, in publication editing, we have these three projects on the right. So the revision of the standard, which will be published as 802.11/2024, and then the 802.11bh and 802.11be amendments. And then just digging into what's currently active. So we have the one TIG, the automotive TIG, and that's developing a report on the automotive use of Wi-Fi. We have an active study group, enhanced light communication. And then we have a number of active task groups. We have TGMF, which is developing the next revision of the 802.11 standard. And then 3 other task groups that, the enhanced data privacy, ultra high reliability, ambient power communications that don't yet have approved drafts. They're still working on their initial draft. So BI does have an approved draft. Actually, that was a very recent occurrence. They've just gone through their initial working group ballot. It passed, and they have an approved draft. And then we have 2 other projects. 11BK, which is enhancing positioning, and 11BF, which is dealing with the sensing. And I'll go into those topics in future slides. So this slide shows mainstream 802.11 evolution, starting with 802.11n, which is known. So shown here, so the 11n, now known as Wi-Fi 4. At the time, it was known as wireless N. 11n introduced spatial multiplexing, 40 megahertz channels, packet aggregation. Packet aggregation is sending more than one user packet in a transmission. 11AC, or Wi-Fi 5, introduced 80 megahertz channelization, 80 megahertz and 160 megahertz channels, 256 QAM, a type of high order modulation that increases the data rate. And it down selected, probably one of the most important things it did was down select on the various beamforming schemes introduced in 11n to produce one variant. So there were multiple variants of beamforming in 11n that were preventing widespread adoption, and 11AC down selected on those and produced one version that everybody could implement. The introduction of the wider channels, particularly the 80 megahertz, and then for later use, the 160 megahertz channels, really incentivized broad support of the 5 gigahertz band. So it's around this time, Wi-Fi 5, that you see broader support of the 5 gigahertz band. So prior to this, the devices were primarily operating in the 2.4 gigahertz band, and then with Wi-Fi 5, we saw broad adoption of the 5 gigahertz band. 11AX, or Wi-Fi 6, introduced multi-user operation. Uplink multi-user MIMO was already part of AC, but 11AX added downlink multi-user MIMO, and both uplink and downlink OFDMA. Then 11BE, on the previous slide I showed that as just having been published, that was Wi-Fi 7. That introduced multi-link operation, which is the simultaneous use of multiple channels. And then finally, 11BN, we'll talk about this in more detail in a future slide, is expected to be Wi-Fi 8. So 11BE, which we, when the project starts, we give these things a name. This one was called extremely high throughput, but now the industry knows it as Wi-Fi 7. This has recently been approved, and products implementing the standard have been shipping for a little while now. And the main feature here is multi-link operation. And with multi-link operation, you get higher throughput because it engages the combined capacity of multiple channels across the different bands. It reduces latency. User data is transmitted on the first channel that goes idle. And you get better reliability and robustness because one channel might experience congestion, but it's less likely that all the channels will be experiencing congestion at any one time. And then it introduced some other features, throughput enhancing features. There's a multiple resource unit, or MRU, which just actually is more of a multi-user feature. It improves the efficiency of the frequency tiling with multi-user operation. And then there's a 4K 496 QAM and the 320 megahertz channels. Both of those two features increase the data rate. And in a typical product, which would be a 2x2 stream, 2x2 referring to the number of streams going into the channel, the number of streams coming out of the channel. So a 2x2 device with 4K QAM and 320 megahertz would give you in excess of 5 gigabits per second. And then just digging into the multi-link flavors from 11BE a little bit more. So when the MN was developed, we introduced at least 4 different flavors of multi-link operation. So there's a single link operation where a device it's implemented on a single radio, and the device moves between the channels. So we would associate on two channels, for example, and then it would move between the two channels opportunistically, presumably based on congestion or other sort of implementation-specific metrics. and it would move between those channels using sort of a variant of the power save protocol. So it would enter power save on one channel and then be active on the other channel, and vice versa. So go into power save on the other channel and become active on the lower channel, for example. So that's the simplest flavor of MLO. Then there's a variant called the enhanced single radio, and with this variant, a device would listen on say 2 or more channels, but it would only transmit on one channel. So you might implement this in a 2x2 system by having one receive chain listening on each of the channels, and then when transmit time comes or receive time comes, you move you switch the change to the channel that's active. So if it's receiving the packet, both chains would be on the channel where the packet is being received, or if you're transmitting, both chains would be on the channel that you're transmitting on. So that's the enhanced single radio variant. And then there's the multi-radio variant. There's the non-SDR, or SDR standing for simultaneous transmit and receive. Here, the protocol sort of provides some assistance, so that you can coordinate with your peer on when to transmit and when to receive. And the reason we want to do this is because a hard problem with multi-radio is leakage from the transmitter into the receiver. So if you're transmitting at the same time you're receiving, typically the noise generated from the transmission will swamp your receiver, and you won't be able to receive anything. So that's a difficult problem to solve in an implementation, particularly in a form factor constrained device. And then there's the SDR flavor. This is the where the device can simultaneously transmit and receive on 2 or more channels. And today, most of the client implementations that support Wi-Fi 7 and MBE are implementing one of the 2 top variants, the single radio variants. This is largely because of the cost sensitivity in the market. The Wi-Fi is a very cost-sensitive market, and adding radios to your device is it's cost prohibitive. And so most of the client devices today are single radio, but we are seeing some sort of multi-radio client devices enter the market, and that's the future. So the future of Wi-Fi is more and more of the client devices implementing multi-radio. Access points, of course, are already implementing multi-radio. Almost all the access points today have multiple radios in them for the 2.4, 5, and 6 gigahertz band, radio each. The difference between the clients and the APs is that the AP, they can have dedicated antennas for each of the bands, whereas in a client, that's form factor and cost prohibitive. And so the complexity of getting SDR to work in a client, there's a lot more complexity, a lot more involved in getting that to work in a client. But there are some out there, and I expect we'll see more and more in the future. And then moving on to 11BN. So 11BN is a fairly new project in 802.11, and this is expected to be the basis for Wi-Fi 8. You'll note that we didn't put throughput in the name. The objective this round is to improve reliability. There's still a lot of legs left, if you like, in the multi-radio aspect. So it'll take some time for the market to catch up and fully utilize the spectrum with multiple radios. Anyway, so the focus here in BN is, and I've tried to list some of the features that I see coming out of the project. This is somewhat speculative. I mean, it depends a little bit on how, what's agreed to, and then again at a later stage, what the market adopts, what people actually implement in their products. So there's one of the topics is reducing the tail latency, and then there's a proposal there known as high priority EDCA. EDCA being the enhanced distributed channel access. That's the protocol we use for accessing the medium. So high priority access for low latency traffic. And the objective here is to try and reduce the tail latency. Tail latency being maximum latency that a user packet experiences from the queuing delay and gaining access to the medium in a congested environment because of other traffic on the medium and because of collisions and so forth. You can experience very high maximum latency in Wi-Fi today, and so this is an attempt to try and reduce that. There's an attempt to reduce the roaming latency. The roaming is where a client device moves from one AP to the next AP. And using multi-link operation to do that. So, for example, you switch one of your channels to the new AP before you break the connection on the other channel with the old AP. So that should improve the latency associated with the moving from one AP to another. There's something that allows secondary channel access while the primary channel is busy. So if you have a very wide channel, 160, even 320 megahertz channel, and the client device itself is not operating at that bandwidth. Maybe it's only operating at 80 megahertz. When the primary channel is so at the moment in the standard today, you always have to occupy the primary channel. That's how all the devices synchronize with each other and know that the medium is busy. And so there's an attempt to change that a little bit so that you can fully utilize the spectrum. So if there's two 80 megahertz devices, one could use the primary channel, the other could use the secondary channel. You get a little bit more medium efficiency out of that. Power save is a big area, is a big concern going forward. We have client power save in the protocol today, and this is an attempt to add power save features to the AP. Historically, the protocol assumes that the AP is always available, and so we're adding some protocol that will allow the AP to enter power save states as well. This is, in enterprise environments or even in your home environments, when everybody goes to bed, the AP often has very little to do. And so power saving in the AP makes sense, and this is an attempt to sort of correct that issue. There's discussion around security enhancements, specifically around control frame protection. At the moment in .11, control frames are not protected. They're sent in the clear. And this opens the protocol to various types of attack. An example would be if a rogue device starts acknowledging data that a device is sending, and then confuses messes up the protocol and causes drop packets and so forth. So there's some discussion around security enhancements, extending the range. There's a discussion around extending the range of Wi-Fi. Here specifically, we're talking about the range as it relates to the sensitivity gap between the AP and the client. So the AP usually has higher transmit power and more antennas in the sense that it has more antennas and maybe a more powerful power amplifier. And the client with fewer antennas, it may be able to receive packets from the AP, but when it transmits in response, those packets may not be received by the AP. And so there's an attempt to sort of reduce that sensitivity gap between the client and the AP. And then finally, multi-AP coordination. This is actually a very, very big topic. There's all sorts of things in this topic. But this is the idea that APs that are near each other can coordinate either to get better frequency reuse. So for as an example, you might devices near an AP can transmit with wide bandwidth, 320 megahertz. But if they're further away from the AP, they might transmit with a narrow bandwidth, and then a neighboring AP can do the same thing, spatially reusing the 320 megahertz, but coordinating on the 80 megahertz, so that the 80 megahertz transmissions to one AP that are further from that AP are not overlapping with the 80 megahertz transmissions to the other AP. Anyway, that's just an idea of what's involved there. There's also far more complicated ideas being discussed as well. And then to get off the mainstream a little bit and talk about positioning. So ranging was introduced in the 2016 revision of the standard in the form of the fine timing measurement frame exchange. This was derived from an existing timing measurement exchange that was used for clock sync. Clock sync in networking devices is important, for example, if you want to support time-sensitive networking or something like that. Anyway, so FTM, the fine timing measurement, was a derivative of the timing measurement exchange, and the purpose there is to sort of measure the round trip time. So on the right-hand side, I give you sort of a rough idea of what this is like. You know, the device would send a fine timing measurement frame to the other device. It would acknowledge it, and if you coordinated the timing, if you accurately measured the timing, and there's actually a lot involved in the implementation here, but you can measure the round trip time or the trip time, if you like, but from one device to the other. And if you do that with more than one peer, you can triangulate and get your position. So that's the essence of positioning in .11. That was so as I say, the fine timing measurement was introduced in the 2016 revision of the standard, and it's been enhanced a bit since then. There was the 802.11 AZ 2022 amendment. This one added support for wider bandwidths, and the wider the bandwidth, the more accuracy you can get on the timing and thus the positioning. So, and then another important addition there was what's called the secure LTF. So that's essentially encrypting the training waveform, so that you can prevent position spoofing, where an attacker comes in and tries to replay or present your position as being closer to the other device than it actually is. You know, one of the applications for positioning is proximity-based security. You can think of this, for example, as opening the door of your car, although that doesn't necessarily have to be a specific. You know, in a computing analogy, computing environment, it might be when you approach your computer, or when two devices are near each other. It would be proximity-based security. You can do different things based on the distance between the two devices. So the secure LTF helps with that. It helps with these attacks, these positioning attacks. So FTM, fine timing measurement, is now widely supported in both APs and clients, and it supports numerous use cases. So geofencing, which would be, for example, limiting access to the network from two devices inside the building. So if you know where those devices are, you can either grant or limit access based on that knowledge. Indoor navigation would be a big one. I mean, we're all familiar with GPS. It works really well, but of course it only works well outdoors. It doesn't work very well indoors. And so using the Wi-Fi access points as for navigation would help with indoor navigation, so navigating inside large buildings. It might also aid regulatory requirements. So for example, the regulators, as they open new spectrum, they might limit the use of the spectrum to indoor only, or there may be various regulatory requirements, regulatory restrictions placed on the use of that spectrum to protect incumbents. And knowing the position of the devices involved in communication may help meet those regulatory requirements. It might help with some of the protocol aspects of .11 itself. So, for example, some of the security, privacy aspects might help with the roaming, for example, knowing when to switch from one AP to the next AP. Rather than doing it based on link metrics, you could do it based on position. It might help with link adaptation. Link adaptation is the part of the protocol, is a sort of the implementation part where you select the data rate, you select the modulation scheme that you're going to use when transmitting to another peer. Positioning itself overlaps with and complements other solutions in Bluetooth and ultra-wideband, for example. And moving on to sensing. So 11BF is developing a protocol to support environmental sensing. These are measurements that are made to monitor environmental changes, for example, movement of people, the number of people present, whether or not a room is occupied. These exchanges are built on the exchanges used for beamforming, for the beamforming protocol, and the protocol developed for positioning. The amendment itself does not define the use of the measurements, it just defines the sounding exchange and the transfer of the channel state information between the devices. There are exchanges involved. So these are exchanges involving 2 or more devices. So the industry has already implemented radar-like sounding in single radios, but these single radio applications don't require standardization because it's not communication between 2 separate devices. It's communication. Well, it's signaling within a device. Example of that actually comes out of my company, Intel, where we have. Where we use the Wi-Fi to sense whether an individual is present or not. So you can, if you're working with your laptop and you move away from your laptop, we can detect that using Wi-Fi, and we can put the system into a low power state more quickly than we could if we were just using timing to determine whether the system is active. So that's sensing. Another project that has actually just completed is 11bh, and this is in the queue for publication. It hasn't been published yet, but it's been approved. This was a short-term project that tried to fix the device identification problem that arises from the use of random and changing MAC addresses. There's been an increasing use of this for privacy reasons in the industry. But it does create some problems. So, for example, the caching of security credentials. When 2 devices meet each other, to speed up the association process, they often cache the security credentials so that the association process is faster. Other uses might be, for example, in a hotel, you register your device with the hotel, using the captive portal, but then your device changes its MAC address, and then the captive portal is like, hey, who's this guy? I don't know who this guy is. You have to re-authenticate yourself. So those are the kind of problems that arise from the use of these, the random use of MAC addresses, the use of random MAC addresses. And so this amendment defines 2 secure methods for device identification. So the first one is referred to as IRM. And with this mechanism, the client tells the AP what MAC address it's going to use the next time it engages with the AP. And then the other mechanism operates from the other side. It's called device ID. And in this mechanism, the AP gives the client an identifier to be used the next time the 2 engage. So both of these mechanisms are based on sharing information securely after association. And that information can then be used when the devices next encounter each other. 802.11bi is a longer-term project that's looking to enhance privacy. So, for example, I've listed a few examples of some of the areas they're looking into and producing fixes for. So the first one would be device fingerprinting. This is identifying a device by the unique information it exchanges prior to association. So, for example, which generation of Wi-Fi chipset it is, what its capabilities are. Does it support 2 streams, 3 streams, or what MCS, what data rate sets does it support, and so forth. And because there's so much optional, there's so much capability information and various other things that are exchanged prior to association, it's possible to almost uniquely identify a device based on that information. So fixing this problem, identifying the identification of a device based on the unique information it exchanges, that's one of the areas they're looking at. Spoofing attacks, an example here would be somebody copies the SSID of a person's home AP and puts that AP somewhere else, maybe at a restaurant the person frequents or something like that. In the work group, we refer to this as the JLO problem from the famous celebrity. So if people want to know where she is, they just copy her APs, her HEM APs SSID, and they put rogue APs around the city, and then when she comes in range of those APs, her device would attempt to associate with them, thinking that they're at home, and thus they would give up her position. So that's the kind of spoofing attack that they're looking at. One of the kinds of spoofing attacks they're looking at. And then the other one is presence monitoring. So this is identifying the continued presence of an individual, but not necessarily knowing who that individual is. So there's some value in that information. So you know that somebody came into a building and has been using the Wi-Fi for so many hours or whatever. That can be useful information. Or how many people are using the network? How many people are in the building? That kind of information. So presence monitoring is another area that this group is looking at. This group has just completed their initial working group ballot. So they have their initial draft 1.0, and the ballot just completed about a week ago, I think. And it was approved, so meaning that more than 75% of the working group think it's in fairly good shape. 802.11bp is a new project looking at battery-free or low-power operation. This is for sort of smart homes, smart grid, smart manufacturing, sort of logistics. They are particularly interested in the fresh food supply chain, so sort of devices that monitor the food, monitor temperature, for example, and report back to databases on the environmental conditions that the food is experiencing while it's in transit or while it's in the warehouse or whatever. So those kind of applications. They expect to sort of define ambient power communications in the sub 1 gigahertz and 2.4 gigahertz band. By ambient power, they mean sort of battery free. So you can harvest energy, RF energy from the environment or from the signal from the transmitter itself. So that kind of communication, or very low power, coin cell battery operated Wi-Fi. It'll coexist with legacy 802.11 devices. Because this project is still in its very early stages, when you get this presentation, there's a link there which will take you to the Topic Interest Group report. So prior to this task group forming, they operated as a Topic Interest Group, and they developed a report on the kinds of applications, the kinds of use cases they want to apply the technology to. 11BQ, this is a task group that has just started, and they are looking at what we call integrated millimeter wave. So the objective here is to simplify the 42 to 71 gigahertz band operation to reduce implementation cost. So we've had 60 gigahertz operation in the .11 standard for some time. It was introduced with the 11AD, 802.11ad amendment, and then enhanced with 11AY and 11AJ. AJ was to tailor it specifically to the China market. AY was sort of general enhancement. With these previous generations, they assumed standalone operation. So it was designed to have a APN client or peer-to-peer operation completely standalone, so only using the 60 gigahertz band, only using the millimeter wave band. And the objective now with this project is to redesign with multi-band support in mind, and that's why, hence the integrated. So with this redesign, we're assuming that the device will already support some low band operation, 2.45 and 6 gigahertz band operation, and that we're adding an additional radio in the 60 gigahertz band. So we expect a lot of architectural reuse from the low band PHY. So one of the problems one of the issues we're trying to solve is market adoption. There hasn't been a lot of pickup as the previous generations, ADA, Y, and so forth, and that's partly due to the expense. And so we're trying to minimize the cost of supporting this. So if we can reuse the low band PHY as much as possible, then you can accompany or produce implementations that where the vast majority of the, they could produce a single design that supports the 60 gigahertz band, the mmWave bands, but the vast majority of their sales might just be in the low band. They only support 2.45 and 6 gigahertz band. And then they add a separate RF component to support the 60 gigahertz band, the mmWave band. But other than that, the baseband itself is common to all those bands. So that's one of the key objectives there. And then to eliminate what's called the control PHY. So there's a special low data rate PHY in the AD design that is used to do the sector sweep. This is where the devices sort of sweep their beams, trying to find each other. And because we are assuming low band connectivity, we could swap that. We could eliminate that operation, or at least the control PHY itself, and coordinate the sector sweep from the low band. So we don't need a special PHY to do that. So those are that's what we expect from that project. And this project would be particularly relevant to China, where the 6 gigahertz band operation is not, the 6 gigahertz band is not available in many parts of the world. So, and that's where this project would be particularly relevant. My expectation is that we'll only see adoption once we see a lot of congestion in the low bands, and that congestion will occur first in China, places like China, where they do not have access to the 6 gigahertz band. We have a study group, Enhanced Light Communication. So the 802.11bh 2023 standard amendment added light communications to 2.11. And this study group is preparing a PAR, a project authorization request, to enhance this work and add multi-link support. And then there's an interesting topic of underwater operation. So, there's increasing use of sea drones, and there's an interest in communicating underwater. And you're probably aware that radios do not work very well underwater. And so using light is one way to solve this problem. We expect the task group, the PAR is actually being reviewed this month, and we expect approval soon and an operating task group in May of this year. And finally, there's a topic interest group called the Automotive TIG. And this group is developing a report on the automotive use of Wi-Fi. So the automotive industry, this is driven by the automotive industry actually, wants to use Wi-Fi opportunistically to update, software, update maps, get updates on road conditions and so forth, serve internet connectivity to the occupants of the car, of the vehicle, and connect the mobile devices. And so they'll be looking into this in great detail, looking at use cases and requirements, key performance indicators, and then technical approaches and gaps in the standard to address these areas. And I think that a summary, yeah. So let's just summarize what I said. It's kind of hard to summarize. There's a lot of threads going on in 802.11, but I try to pull them together on the slide. So what to expect going forward? So expect improved performance as devices make more efficient use of the available spectrum. So as they adopt more, as we see more adoption of multi-radio designs, then operating more bands, 2.4, 5, and 6 gigahertz bands initially, and then later in the 45 and 60 gigahertz bands, using wider channels, and then the more complicated schemes that for puncturing to work around interferers and incumbents in these bands. Expect more robust operation with lower latency. So you can get this from the simultaneous use of more than one channel. You will see lower latency from improved channel access techniques that are currently underway in VN. NPCA stands for non-primary channel access. That's that secondary channel access mechanism I referred to, and then high priority EDCA. New applications. So in the sub-gigahertz band, operation in the sub-gigahertz band, there is a version of .11 that operates there, 11AH. There are implementations using that. Live communications, there are applications there as well, applications of the 11BB standard, primarily military at the moment, because of the immunity to jamming and eavesdropping, and then very low power applications from the outcome of the DP project. So new features, and also expect new features that are not directly related to communication. So, for example, indoor navigation, proximity and position-based security, environmental sensing, and enhanced privacy. And with that, I think I've reached the end of my slides, and I think we'll have some time for discussion and questions.
Thanks again, Robert, for the very informative presentation. And you're right, there are already a list of questions in the Wellback checkbox already. But for the first question, be honest, I believe I'm not sure if you can answer it or not, but we can ask Ego2 internally about this, because this is a historical question. The audience asked why the Ego2.10, the link layer security mechanisms, was withdrawn in 2004. At that time, I was not involved in Ego2 yet. Perhaps, Robert, I'm not sure if you remember why the link Ego2.10.
I'm going to have to punt on that one because I was not present and not involved in that at all. So I'm not sure why. My guess would be the relevant applications weren't there. You know, .11 has its own security mechanisms. I'm not sure what .10 added, but yeah, to be honest, I don't know why .10 never went anywhere. It's not the only one that hasn't gone anywhere. We do have a number of work groups that have formed in 802 and then disbanded. So
okay, don't worry. And then there are some discussion about the 320 megahertz in the checkbox. As Robert, you know, for Wi-Fi 7, we actually have the 320 megahertz. The audience say that in your slide you also mentioned 320 megahertz in the Wi-Fi 6. Perhaps you may.
Did I mention that? I hope not. Let's go back to that quickly. Oh, well, that would be an error. Actually, I think I meant to put it in the 11bi row. So yes, I'll correct my slides for that. That's an error. They added 1024 QAM and 6 gigahertz band operation.
Okay, great, thank you. So, and then another question. I forget the long name, but some of the audience may not know. But the question is: any plan to include L4S into the Ego2.11? I forget I forget the full name of L4S. Also, I know what it is.
There is work around that. There isn't a task group or a subgroup that's specifically focused on that, but it does come up from time to time. There are individual presentations on the topic. We actually have a liaison with the WBA, the Wireless Broadband Alliance, around this topic. They have I think a whole task force involved in quality of service. So yes, there is activity in that area. Whether that's going to whether that needs or results in any standards change, I'm not sure. I know that some individuals are looking at out-of-order delivery, supporting out-of-order delivery as part of the .11 standard. We don't do that at the moment. We have in-order, we only support in-order delivery. There are ways of working around that with multiple what are called traffic identifiers. But the short answer, I guess, is yes, there is activity around L4S.
Okay, great. And then another question is like, okay, Ego2.11, now we have different task group, different amendments. There are great lists of upcoming features. So the question is, how are they all going to work together with proprietary AI from chipset vendors? So more or less, like standardized solutions together with proprietary AI. So from your personal point of view, Robert, what's your opinion on that?
Again, the working group itself actually has a standards committee that is looking at AI ML. They produced a report. There's a report available on what they looked at. The most interesting areas for us would be, scheduling, beamforming, what else? Sensing, for example, is an area. Let me switch to sensing, which relies on AI. AI techniques. That's the whole. The benefit there is only gained from the use of AI techniques. However, I mentioned that we only deal with the lower layers. We deal with the Mac and the Phi, and in all these things that I've mentioned, there actually is no need. We haven't sort of seen a need for standardization. If we do see a need for standardization, sort of figuring out, if we have to do things in one way, most of the time, the standardization is usually around the transfer of information between the devices. So, for example, in the sensing application, in the standard, we're not going to say, well, this is how you determine the number of people in a room. This is the technique that you use to do that. That's not our job. There's a lot of much smarter people. There's a lot more people out in the industry that can figure that out. That can apply AI in ways that sort of provide those that differentiate themselves in the industry and provide those features. What we're trying to do is we sort of look across the ideas and see what's necessary from a protocol perspective to support those ideas. So that's what they're doing in BF, for example, is they're defining the protocol itself for measuring the environment, for sounding the environment, and they're defining the protocol for exchanging the resulting measurements between the two devices, transferring the information from one device to the other. How that gets transferred up the stack and how that's actually used, that's not something that we need to get involved in as a standards group in this particular organization, in this particular application, I should say. If we do see an area where we do need to get involved, of course we will get involved. But so far we haven't seen a compelling area where we need to get involved. So the other example I brought up was smart scheduling, or another area might be like smart use of the spectrum, channel selection, or deciding where and how to use the spectrum in a particular environment. These are all areas that are prime that are open to AI techniques, but as a group, we haven't sort of seen any need for us to get directly involved in defining how you do that. If we do see a need for standardization, we will get involved. But as I say, typically our involvement would be in the exchange of information, or in the something we need to do over the air.
Okay, great. So perhaps we will soon pass the hour mark. We will answer 2 more questions. And actually, one question I see multiple participants may want to know is, Robert, can you give a high-level overview in 1 minute? What is MLO?
I tried to do that.
Yes.
So MLO,
because this is the very important component of Wi-Fi 7.
Think of almost all the throughput enhancement in Wi-Fi, in wireless communications in general, comes from the use of more and more spectrum. Okay. The problem with spectrum is there's a limited amount of it, and it's all been allocated. It's already almost all in use at the moment. It's not in use in very efficient ways. And so when we get regulatory approval to open a new band for use by Wi-Fi, it's usually unlicensed use. We usually have to work around incumbents. We usually have there's restrictions to that spectrum. Anyway, MLO is just a smart way of using spectrum. You're not going to get a 1 gigahertz channel. It's not available. We're not going to get a 1 gig. Well, maybe in the 60 gigahertz band. But anyway, in the low band, there isn't that much contiguous spectrum available. And so you can think of MLO as a smart way of using spectrum in smaller chunks. So what we're trying to do with MLO is not be constrained by not preventing what's happening on one channel from affecting what's happening on another part of the spectrum. So if you want to transmit in one part of the spectrum, you should be able to do that, even if another part of the spectrum is busy. So think of MLO as just increasing the effective bandwidth of the device.
Okay, great. And then the last question of the day, there's a question about rather there is any new activity on the IBSS ad hoc wireless network, at least inside the scope of Echo 2.11, or any thought on that?
So the history of .11, yes, we had IBSS. These are ad hoc networks where a device, a group of devices in an area could get together and form their own network. It fell out of favor at one point, and it's actually deprecated in the standard in favor of infrastructure use, because we can even the peer-to-peer mechanism that the industry ultimately adopted is referred to as Wi-Fi Direct. But that's essentially where one device becomes the master and the other devices are clients to that master. And that was easier to support, easier to implement than the more generic one. At least, the generic one is nice. The independent one where anybody can be the master is nice. And it's more robust. It allows any device to enter and leave the network as you go. But it was hard to support at an application level, for users to sort of set these things up. So we went to the Wi-Fi Direct way. That has some success. It found use in printers and things, devices that needed a peer-to-peer connection for specific uses. There's the Wi-Fi Alliance has another peer-to-peer technology called NAN, or neighbor-aware networking. That is actually closer to what IBSS was. So, one of the devices, it's a little different in the sense that one of the devices is kind of elected a master, but the network itself is robust in the sense that devices can join and leave the network pretty easily. That's seen some adoption in a proprietary way in Apple's products. They use it in their what they now call AirDrop. Interestingly, their original version of AirDrop was Wi-Fi Direct based, and their current version is NAN based, Wi-Fi Ware based. Yeah, so I wouldn't be surprised if we see it come back to .11. There may well be problems with the current peer-to-peer protocols that require us to address them in the .11 standard itself. That hasn't happened in the past as well. For example, I'll give you an example. The OWE encryption standard was standardized outside of .11 and then brought back into .11. And now we own that and manage that. Peer-to-peer operation currently defined outside of .11. It may well come back into .11, and we may work on it again.
Okay, great, Robert. I hope you don't mind. This is really the last question, because I forget to type two posts, and then there is a question before I type it. The participant asked, how do you see the coexistence of Echo 2.11 and XG Telecom? I mean, the cellular. So all in all, it's more like the how do you see the coexistence of Echo 2.11 and also the cellular network, like GE or the others?
Historically there's been a bit of tension between, shall we say, 3GPP and 802.11, but that has all gone away. Is largely going away. I think 3GPP is recognizing, that their use case, their application is outdoor, long distance, mobile uses, and they're recognizing that indoor, not so mobile, high throughput is our domain. certainly the operators are recognizing this and deploying products in this manner. So you'll see a lot of the cellular equipment suppliers often integrate Wi-Fi into their equipment, for example. There were attempts in 3GPP to do indoor versions to use unlicensed spectrum and so forth, and most of that has not sort of gone anywhere. I mean, there's been very limited adoption of that, and so I think we've always been focused on indoor only, on indoor sort of low mobility applications, short range low mobility applications. That's been our focus. We've never sort of deviated from that. 3GPP have tried to enter that space. I don't think they were successful. I expect we'll see more closer and closer cooperation between 3GPP and 802.11 on handover on some of the problems, the real problems that we do experience. So that end users experience. So people often move from inside a building to their cars and so forth, and they want a smooth handoff between cellular and Wi-Fi. I think there will always be separate technologies, at least as far as I can see in the future. But another thing to recognize is that 3GPP has also moved closer to the 11 in a lot of ways. I mean, they used to have a very a session-based architecture, if you like, based on tunneling between, for specific for authentication, for quality of service and all this, and they've moved to a much more open packet-oriented architecture. In fact, they've adopted, if you look at their SA architecture, they've adopted .3, so Ethernet. They widely use Ethernet at their back end, and that, with their shift to a more packet-oriented network, they're more compatible with us, and we use very similar security protocols. So there's no reason why we can't make handoff between cellular and Wi-Fi work better. I expect we will do in the future.
Okay, great. Good answer. Thank you so much, Robert. Okay, so now it's the end of our webinar. Once again, I would like to express my sincere thanks to Robert for joining us today. This is a great presentation with lots of great feedback from the participants. You can see from the Webex chat box and sharing with us what's going on in the world of the 802.11. So for those on the call, if you are interested in participating and contributing to standard activities, you can actually visit computer.org for more information. And for 802, you can browse www.IEEE 802.org-11, including all the information about the ongoing projects. A quick programming note. Our Computer Society will host 2 standard webinars in April. One is related to blockchain and another is related to AI and metaverse. You will soon receive more email details about these 2 webinars in our member communications. So once again, thank you so much, and thanks for all come and attend this very informative presentation. And once again, thank you, Robert, and all. Please have a great rest of your day. Thank you.
Pleasure. Thanks so much. Thank you.
Thank you all.